So, nobody stepped out. Okay. I was trying to figure out what to put in the exam exactly next week. So, our lab that is going to cover LEDs is not next week; it's the week after, which is a long time from now. So it doesn't make sense to wait to do the lab. So we're just going to have everything up to 24C on the exam. So we're going to finish 24C today. We're going to talk about the solid solutions. We're not going to get too much into the LED stuff, but we'll talk a little bit about we've already started talking about colors of light emitted from a band gap. So that's pretty much it. And then when we come back from the week of, like, we have a day off on Tuesday, and then we have Thursday as our exam. So the week after that, we'll start the new stuff. We'll do the lab. It'll be neat, but it'll be too late to supplement your learning. But it's okay. It'll be neat. As far as studying for the exam goes, I don't know if we'll have much time to talk about it today, or to go over it today. But I posted in the exam prep folder on the side, so at the very bottom, exam prep, in the content area, is a review sheet, a practice exam, and a key for the practice exam. The review sheet basically just has the sections we've covered, and then it's got bullet points for all the different topics that you might want to kind of look at, make sure you understand. And the practice exam is great. So this is the key one, so it's got everything marked off. It's going to look a lot like the exam we're going to take. I've marked off a couple questions that wouldn't be on the exam, but other than that, this is pretty similar. Notice that you get all the pictures you're going to get that I said you would get. So body center, cubic, all that. Equations, conversions. We've got the equations for the side of a unit cell, if it's simple cubic, body center cubic, so forth. I did say we're not going to calculate packing efficiency, but that's there anyway. Yeah, so feel free. We would normally go over it on Tuesday, but since we don't have Tuesday, you guys are going to do it yourself. I will be in here for office hours Monday morning. And then since, I guess we don't have lab on Tuesday. Wednesday, I also don't have labs. I canceled the Wednesday classes lab for the same reason. But I will be here Wednesday morning. So if you want to stop by Wednesday morning to go over some stuff, we can do that as well. Okay. Yes?
Just wondering if the Thursday morning office hour is still on.
Yeah. Sorry.
Okay.
That's still good. Yeah. All right. The homework is a little bit screwed up again. I need to fix what is due this coming Monday, but the 24C is definitely going to be due. The 25, Chem Activity 25, we haven't started that yet. We're not going to start it, so that's not going to be due. I need to take that off. And I need to double check to see what Mastering Chemistry is telling you to do. So if it's any of the intermolecular force stuff, don't do it yet, because we haven't covered any of that yet. So just do up to the stuff we've learned so far. But I'll fix it officially. You should see a change soon. All right. Let's see, where are we? So we've talked about, let's go back from the beginning actually. We've talked about this band gap. We've talked about how to calculate photons emitted from an electron dropping from the conduction band to the valence band. And then we talked about, well, what affects that band gap? So let's review that real quick, because we went over this on Tuesday. Tuesday. So first we looked at just plain old group 4 elements. And the biggest, there's a couple factors that are changing here, but notice that the band gap is getting smaller as you go down the periodic table. Why could that be? Well, one thing that's definitely changing is the unit cell dimensions are changing. They're getting bigger, and that's because the atoms are getting bigger. So when your bond lengths are getting longer, your band gap's going to go down. Why does that happen at the atomic level, though? Well, it's all about overlap of orbitals, right? So the longer the bond, the bigger the atoms involved, the worse the orbital overlap gets. And remember that band gaps, and bands by themselves, are based on molecular orbital theory. If I've got a single 1s orbital overlapping with another 1s orbital, they will make two molecular orbitals. They'll make a bonding and an anti-bonding molecular orbital. And the splitting, so the fact that this is going down in energy and the anti-bond is going up in energy, is based on how good the overlap between these orbitals are. The better the overlap, the bigger the splitting is going to be. The worse the overlap, the less small the splitting is going to be. And so tin, which has large atoms, long bonds, and so bad orbital overlap, has poor splitting between the bonding MOs and the anti-bonding MOs, which means that the valence band and the conduction band are not really split. They're kind of right on top of each other. There's no gap between them. So less than 0.1 electron volts. But carbon has very good overlap, and so the band gap is giant. Okay, so that's one factor to look into, is just the size of the atom. That'll tell you a little bit about what's going to happen to the band gap. Then we looked at solid solution, or not solid solutions, isoelectronic solids. So these are group 4-like compounds. Now I'm going to preface this by saying we can make semiconductors out of lots of things. We are focusing on a very narrow range of semiconductors, ones that are isoelectronic with group 4. Why? All of these group 4 isoelectronic compounds are similar crystal structure. They're diamond-like or zinc blende-like, however you want to call it. And so that we're limiting the factors that are changing, so we can kind of accurately predict what else is happening by other reasons. So notice that the size of the unit cell is pretty consistent. So if the size of the bond lengths are not changing, well, what else could be affecting the band gap? So because the band gap is obviously changing, well then we kind of looked at other factors. One factor might be difference in electronegativity. So two germaniums that are next to each other will have 0 difference in electronegativity. But as you go down this group here, copper and bromine have a very big difference in electronegativity. And that might be what is affecting the band gap. So the other thing that you could describe about this as well, the other thing that you could say about compounds that have a large difference in electronegativity is that they have large ionic character. The bigger the difference in electronegativity, the more ionic the bond is going to get. All right, so remember more ionic, which means more localized electrons. The electrons are more tightly held on to the particular ions involved. They're less metal-like. Metal-like meaning the electrons are loose, can go anywhere they want. All right, so we went over that. Then, well, coming back to this idea, well, what if so we can make LEDs we can make lots of things, semiconductors. But one of the things we like to make out of semiconductors are LEDs, because we take advantage of the idea that if I have a material that has this band gap between the valence band, and this is full of electrons, okay, so just more than just that, it's filled with electrons. This is empty, this is the conduction band. And there's no electrons in it. Well, if I could give this a little bit of energy, electricity for instance, I hook it up into a circuit, I can cause some of these electrons to move up here. So I have a few electrons moving around the conduction band. All excited electrons, that's what these are, these have extra energy, they're excited. All excited electrons will eventually relax. They will go back down to the ground state, their lowest energy state possible. And when this electron drops back down, it's got to give up that extra energy, and it'll give it up in the form of photon. And that photon energy will be exactly the band gap energy. So we make LEDs out of these things because the LED, the light that is emitted, comes from these electrons relaxing. And so the light of the LED is based on the band gap. So here I've got some LEDs that I could make that have approximately kind of bluish lights. These are definitely in the blue region. But what if I wanted to make some green light or yellow light or something like that? None of these do yellow. This is kind of reddish, barely reddish. It's like more infrared. So how would I make something like that? Well, I would start to play with, I could try other combinations of atoms, and so instead of gallium and arsenic, I could maybe use gallium and phosphorus instead, or I could use gallium and nitrogen. But an even better idea is a solid solution, because we're not dealing with an ionic compound. We don't have, if I mix two different elements, for instance, in an ionic compound, sodium and chloride, I have to have a 1-to-1 ratio, 1 sodium for every 1 chlorine, because these are ionic. I have to balance out the plus and the minus. But for something like this neutral semiconductor, it doesn't really matter how much silicon versus germanium I put in. They're neutral. This is like making an alloy, all right, like we did in lab 1. I could do any proportion. It's, that's a quarter, a fifth of silicon and 4/5 germanium. Doesn't matter. And silicon and germanium each have their own band gap, so if we mix them together, we could maybe make a band gap that's somewhere in between. And we need to be able to learn how to write the generic formulas for these compounds. So if I have an X amount fraction of silicon, the amount of germanium I would have to have as a result is 1 minus X. So this is 0.4, this is 1 minus 0.4, 0.6. They have to add up to 1, okay? So here is a visual, and I think I showed this to you, but here is the visual of, different mixtures of silicon and germanium. We've got pure germanium here, we've got pure silicon here, but you can have any mixture in between. And again, it's not like an ionic compound. They don't have to be perfectly spread out. It's chaotic, it's random. They're kind of well distributed, but it's not perfect, right? You can have little clumps here and there, it's fine. That's what it's going to look like. So I mentioned, well, what about using other? So when we make these isoelectronic materials, we do, for instance, a group 3 atom with a group 5 atom. And if I have equal amounts of those, I will have something isoelectronic with a group 4 atom. So gallium with arsenic. But I could do gallium with phosphorus too. I could do gallium with nitrogen. That's a group 3 and a group 5. But if I do pure gallium arsenide, I get a reddish LED, kind of more infrared, but reddish. With gallium and phosphorus, I get a green LED. With gallium and nitrogen, I get a blue LED, and that's it. So how do I get yellow? How do I get orange? Well, that's where the solid solution comes in. I can still do a solid solution even with these isoelectronic materials. I could mix gallium with a mixture of phosphorus and arsenic. But the ratio of those two amounts of group 3 and group 5 still have to be 1 and 1. I have to have equal amounts of group 3 atoms and group 5 atoms. So notice that I have 1 gallium, and if I add up the group, the phosphorus and the arsenic, 0.4 and 0.6, I get 1 of the group 5 atom too. And here's the math if you care, but that's in your packet. So the generic formula for a solid solution using this isoelectronic material, where you mix up phosphorus and arsenic, is 1 gallium, right? There's nothing there, it's a 1, with X amount of phosphorus, 1 minus X arsenic. Yeah.
Just wondering, does it have to be gallium or just any group 3?
It can be any group 3, yeah. So gallium, you could mix aluminum, you could do indium the other way.
Huh.
Yeah. And you could do 2 steps over, just like we did. Like you could do zinc with selenium. You could do zinc with sulfur, zinc and oxygen.
As long as it's 1 to 1 with the composite of 3 and 5.
Yeah.
Does that mean you could mix the cation, or not the cation, the group 3 as well? So it could be
Yes, definitely. So you could have a mixture. You could have 3 of those group 3 together, mixed together, as long as they add up to 1. Yeah. So honestly, this is where you get like infinite possibilities. You can really tune your LED. And this is how we make the LEDs. This is how LCD screens are made. They come up with a semiconductor that makes the perfect colors for your computer screen that'll mix red, blue, and green. That'll mix together to make, you know, the colors you see in your monitor. The new technology, it's not new, but quantum dot QLED. So instead of using a mixture of different elements like this, like solid solution, they grow pure, what do they do? It's cadmium selenide, CdSe. So cadmium selenide, it makes one color. But if you make it nanoparticles, then it changes the properties. And you can tune it to any color you want based on the size of the particle. It's weird. We're not going to cover that, but that's the QLED, the quantum dot, which are nanoparticles. That's the Samsung thing. It costs like $5,000. Like, I don't know. It's ridiculous, but they look nice. They look really nice. Okay, so let's try the questions in this section, 46 to 53. I believe it's page 55. And let's just go through the questions, make sure that they make sense as we're thinking about these solid solutions. This is about as far as we're going to get in terms of like understanding LEDs and that stuff. If you want to learn more, take a material science course or something, or engineering, something like that. It's a nice intro to it. geeky. Why not?
That sounds so bad.
You have to take a one PE course at high school, like this geek summer school.
So many words.
Yeah. I also went to Jesuit High in New Orleans for freshman year. That's a different ballgame. Full uniforms, khaki name tags, black shoes, all boys. It was awful. It was awful. There's so many bad kids there. The schools at New Orleans are like the worst. They're the worst. Yes. So remember when we were doing just regular formulas, if I had 1 mole of sodium chloride and I broke it apart, how many moles of sodium ions would there be? So if I had 1 mole of sodium chloride, and I want to know how many moles of sodium ions were. Well, we look at the formula and just say, well, for every formula, there's 1 sodium ion. So there should be 1 mole of sodium ion for every 1 mole of sodium ion. It's very basic equation.
We don't need to do anything.
Yeah. So in this case, it's if I have a mole of that stuff, there's going to be a mole of gallium in it.
But with these two, it's gonna be that much.
Fraction.
Oh,
yes.
okay, yeah.
Mhm.
Because they're both bigger 5.
Yeah, exactly.
Okay. And then, but then how you
Yeah, so you can build these mole ratios based on the formula itself. So for every 1 formula, there's
Making it
this many
harder.
things. Yeah, it's okay.
how many moles of gallium do you have?
Thank you.
Yeah. Moles are always tricky. People forget it's just counting. It doesn't seem like it sometimes. That's why.
Oh, because you already said that atoms are split between arsenic and phosphorus, and that's 1. And then that makes sense. And then how many moles of phosphorus does that become to 1 mole?
Well, but it's already 1, so it's a weight one. It's 0.4 out the
All right.
Oh, so you are like.
So let's talk about the answers because I think some people are forgetting some of the basic stuff, which is fine because it's been a while. If I look at a mixture of gallium or this stuff, I'm not even going to say what it is because it's hard to name these. What fraction of the total number of atoms have 3 valence electrons? Well, the gallium has the 3. Everything else has the 5. And it's in a ratio, so there's 2 total atoms, right? 1 of the gallium, and if I add up the other 2, that's another 1. And the gallium is 3, so this 1 out of the 2 has 3 valence electrons. So that's 1/2 of them, okay? Now number 7, I kind of did it over there, but the idea is if I have 1 mole of gallium, this stuff, AS26. Well, this is making a mole ratio from the formula. So you'd say, okay, if I have 1 formula, all right, and let's just scale it up. Instead of 1 formula, 1 mole of formulas, and the formula is gallium 0.4, arsenic 0.6. How many galliums are there in there? Well, it's 1. That's what the formula says. There's 1 gallium. So there's 1 gallium or 1 mole of gallium if I scale it up. So look at the math. It's just 1. I have 1 mole of gallium in 1 mole of this substance. All right, so nothing fancy here. But as far as phosphorus, well, only got 0.4 inside the formula. So 0.4 moles of phosphorus in this formula. I'm just going to put the hash marks there. So 0.4 moles. And then for arsenic, 0.6 moles. And yeah, so that's how it's going to work. And so this should make sense, because if I were to ask you, well, if I have 1 mole of this compound, how many total atoms are there going to be? There should be 2 moles of atoms. Right? One of these formulas should have 2 atoms at all. So if I have 1 mole of these formulas, I should have 2 moles of atoms. So there's the 1 mole of gallium, I didn't write equals, plus 0.4 moles of phosphorus, plus 0.6 moles of arsenic, that is the 2 moles. Okay? Okay. So, what is the general formula made from gallium, phosphorus, and arsenic? Well, since we're not changing gallium, that's going to stay the way it is. And we're changing phosphorus and arsenic, so let's say phosphorus is X. Whenever I make this, the arsenic has to be 1 minus X. So if this is 0.2, that's going to be 0.2, 1 minus 0.2, 0.8. All right, so that's, just a basic understanding, how to understand what you're seeing, how to write these formulas in general, so forth. So which one has a larger unit cell length? Gallium arsenide or gallium phosphide? So larger unit cell. So bigger unit cell. The arsenic one, because gallium is the same between them both, but arsenic is a bigger atom than phosphorus is. So gallium arsenide should be a bigger unit cell. So we'll get to, well, which one is more ionic in character? I can barely hear you guys. Gallium phosphide is going to be more ionic, and we know it's more ionic because there is a larger difference in electronegativity. So phosphorus is more electronegative paired up with the lesser electronegative. It's going to be a larger difference in electronegativity. So which one's going to have the larger band gap? Gallium phosphide, yes. So remember, you get small band gaps the larger the unit cell. So gallium arsenide by unit cell is going to be the smaller band gap, gallium phosphide larger, but you get a larger band gap with more ionic character, larger difference in electronegativity. So for both reasons, larger band gap for gallium phosphide. But let's translate that to solid solutions. So if I start making a solid solutions and I have these formulas, well, which one's going to have the largest unit cell length? Which one's going to be the smallest? So here's one to kind of fixate on maybe. This is basically saying 1 gallium and that must be a typo. I think that's a typo. Yeah, it's got to be a typo. Sorry. So imagine the first 0 point is not there. Get 1 gallium and 1 phosphorus and 0 arsenic. That's pretty much pure gallium phosphide. So if you have gallium and just phosphorus versus a little bit of arsenic mixed in, well, arsenic is a bigger atom. The idea is the more arsenic you're going to mix into it, the bigger the unit cell is going to get, on average. So this is going to have the smallest unit cell length, and this one right here, the one with 0.6 arsenic, that's got the highest amount, that's going to be the largest unit cell length. Why would we care about this? Well, now we can predict band gap. So which one's going to have the larger band gap? This one down here will have the larger band gap. The smaller unit cell length should have the largest band gap. This one's going to have a smaller band gap, and it should go, this one, sorry. And as you go down the line here, the band gap is going to get bigger and bigger and bigger. Okay. So the idea here is we're tuning LEDs. We're tuning the band gap. We can change it to whatever color we want now based on the amount of each element we're picking to create our LEDs with. So let's just keep going now and answer questions 54 and 62. And this will kind of show some pretty good questions that you'll see on exams, kind of things like that. Okay. Actually, let's just all do it together because I feel like people are a little tired today. So let's just do it on the board. You're welcome to ignore it if you want. But so the first question here is talking about these elements. We have unit cell dimensions. We have this empty column called bond dissociation energy, which it means exactly what it says. It's the energy required to dissociate, means separate the atoms. So you're basically breaking the atoms apart. You're breaking the bond. And so we have these band gaps here that go along with the unit cell dimensions. We have two ways now to kind of understand how strong a bond might be. All right, we've already known that the shorter the bond length, the stronger the bond. But now we have this added property of band gap. The larger the band gap, the stronger the bond's going to be. And so here you can see that, hey, short bond or large band gap, either way, that's going to be the strongest bond, which makes sense. Diamond has very strong bonds. It makes covalent networks, or strong covalent networks. It's a really hard substance. So it should have the largest bond energy. It takes a lot of energy to break the bond. So 346. And these are in lines, in order. So it's going to go down the line. After that, it's 222, then 188, and then 146 at the bottom for 10. All right, so this is just understanding we have now multiple ways to judge a bond energy, okay? So 55, we have this statement. We have to decide if it's true or false. As the size of the atoms increases in a solid, the band gap energy also increases. True or false?
Right. Say that again, false.
As the size increases, the band gap increases. False, yeah. So think about that for a second. And you can see it right here. As the size increases, the band gap decreases. All right, so the bigger the atoms are, the more metallic they're going to be, the lower the band gap's going to be, okay? Here's another chart that we've seen already. We never actually calculated any numbers, but we looked at the difference in electronegativity. So if we fill this in, germanium, a germanium with another germanium will have 0 difference in electronegativity. That's one of the answers. And then as we go from gallium and arsenic to zinc and selenium to copper and bromine, the difference in electronegativity is just going to increase. So 0.4 next, then 0.8, and then 0.9 at the end. And you can see that the difference in electronegativity is also a measure of how ionic it is. The more ionic it is, the larger the band gap is going to be. Okay? The less metallic, more ionic. So, when we get to 57, we are plotting those 4 materials that we saw in the previous graph. We have Y, on the y-axis we have band gap, and x-axis is blank. But what was changing the band gap? It was the difference in electronegativity. So that's actually what belongs in this x-axis, is difference in electronegativity. If you have 0 difference in electronegativity here, that's where germanium is. When you have a large difference in electronegativity, 0.9, that's here, copper and bromine. So that's what's missing. And the argument is that the band gap, e.g., band gap varies with atomic size. The other student argues that band gap varies with difference in electronegativity. In fact, they're both right. Okay, so band gap will change on both. If the atoms change size, they'll be less. The bigger they are, the less overlap, the smaller the band gap's going to be. Or the bigger the difference in electronegativity, the higher the band gap's going to be. Right? So both of those factors will affect band gap. All right, so here's another one. True, well, not true or false, but completing the sentence. For solid solutions, the band gap energy for a solid solution will do what? Increase or decrease as the bonds between the atoms become more ionic. Yes. So as your atoms are more and more ionic in a solid solution, the band gap will increase. So 59 is the one that I was thinking about when I said, oh, this is a good test question. I mean, they're all good test questions, but this is a good one for like making you sit and think for a little bit, work it out. So which one of these are valid solid solutions? Valid meaning that will make a group 4 isoelectronic species. Yes?
I'm getting a little mixed up on this one. Let me try to have it straight. So, electronegativity is proportional to the band gap.
Yeah, roughly, yes. Yes.
And the bond length is inversely proportional to the band gap.
Yes.
Okay.
Yes.
Thank you.
Okay, so 59, which one of these are valid, which ones are not? So the way I like to do these is write them out, or I'm going to write them out just so I can write on it. And kind of label every atom and what group are they in? How many valence electrons does each type of atom contribute? So gallium, it's in group 3. It has 3 valence electrons. So I'm going to write 3 on top. Aluminum is also in group 3. And arsenic is in group 5. The idea is we want a compound that is going to average out 4 valence electrons. So you need 1 of the group 3, 1 of the group 5, and as long as that works, then the formula makes it work like that, then it's fine. And if you can't see it with these, algebraic notation, put a number in. So if I make, for instance, x, if I make it 0.2, then 1 minus x, 1 minus 0.2 is going to be 0.8. And you can see this adds up to 1. I'll have 1 of the group 3, and I'll have 1 of the group 5. That's perfect. That works. This is isoelectronic with a group 4 species. So we keep going. I think you can see B works. Gallium, that's the one we kind of solved in the work. You're keeping 1 gallium, and then you're varying phosphorus and arsenic. They're both group 5. So B works as well. But let's do C. Indium, aluminum, and phosphorus. So indium, probably never worked with it ever. I haven't, but it's group 3. 3 valence electrons. Aluminum is also group 3, and phosphorus is group 5. So again, if you want to replace your algebra with some real numbers, let's do it. 0.2, why not? That's going to be 0.8 if I plug 0.2 into x. So you can see that this is 1, but this is also a group 3. So I'm going to end up with 1.2 of the group 3 and only 0.8 of the group 5, which is not 1 and 1. This is not going to average out to 4 valence electrons. It's going to be slightly lower. So this is actually a bad one. This is not isoelectronic with all the group 4 elements. What are the consequences? It's not, it might be conductive, it might be a semiconductor, it might work, but it's not going to have the diamond structure that we're used to. It's going to be a different compound altogether. So it doesn't work. It's not isoelectronic. The last one is a kind of a doozy. ALX gallium, 1 minus X, 0.5, indium, 0.5, and then phosphorus. So again, do the same thing. Just kind of label everything so you can see it. This has got 3 valence electrons, this is 3, this has got 3, and that's got 5. So 1 of the 5, so far so good. The way this works, I mean, again, if you want 0.2, that's going to be 0.8, real numbers. This will add up to 1 of the group 3. But then the 0.5 in the parentheses out here is basically say only half of that added to half of this, still group 3. I get 1 total group 3 atom out of all this. Right? So this adds up to 1, but I only take half of it, added to half of this, I get a total of 1. So this works. This is isoelectronic with a group 4 species. So this one's a little bit weird to look at, but it does work.
So you can like tune the band gap pretty well with these, but can you get extreme changes in their like electronic properties, or is that something that you have to be on the nanoscale for?
So I guess there's a couple of considerations. I mean, we're operating under the assumption that as long as you do group 4 isoelectronic, you will have a material that's going to be, for all intents and purposes, identical to anything group 4 like, which is not always true. So, and I guess in extreme cases, maybe it'll make a different crystal structure. Who knows? You have to test it. And then, you know, you can tune the band gap, but at some point it'll stop being semiconductor-like, and you won't, like, you can't make an LED that will emit like high-intensity UV light, because at some point it's going to become insulating, and when you try to give something like that a lot of energy so that it can put the electron up at the top and have it drop down, other things will happen. Like it'll start reacting with air. It'll start. I think there's like a breakdown, like in electroengineering terms, there's like a breakdown voltage or something. There's lots of other things that'll happen before what you're thinking is going to happen is going to happen.
Yeah. Okay.
So yeah, the extreme conditions are always hard to gauge. So this is the general, hey, this is what we expect, and it works for most things. Okay, so 60. If we created an LED that was orange in color, well, so we know how to tune it now, but an impractical way of tuning an LED, and we're going to do this in the lab, is to cool it with liquid nitrogen. We will do this. So if you put a lit orange LED into a cup of liquid nitrogen, what's going to happen to it? What's going to happen to the color? So do you think that the atoms would get closer or further apart if you cooled it? They should get closer, because if you imagine what's happening to atoms at room temperature, yeah, they're in a solid, but you saw in the computer program they're kind of vibrating in place. And if you cool them, they'll vibrate less violently, which may allow the crystals to like shrink. They can get closer together if they don't vibrate as much. So the atoms will get closer together. What happens to band gap when they get closer together? Goes up. Goes up. When the bond length shortens, the band gap goes up. The overlap of the orbitals gets better when they get shorter bonds. And so, would the orange LED turn yellow or red? So band gap goes up. So it's currently here. Which way is more energy, which way is less energy? So if I put ultraviolet here and infrared, this is higher energy over here. This is lower energy. So if the band gap is increasing, the energy of the photon is going to be higher energy. So instead of seeing yellow, you'll start to, instead of seeing orange, you'll start to see yellow. And it'll turn green eventually, and maybe even blue. It depends on how how much the crystal shrinks. So yeah, you'll sit there and it'll be red or orange, and it'll slowly go through all the different colors as it cools down. It's pretty neat. All right.
Wait, so just to be clear there, you said that the band gap will increase,
Mm-hmm.
and so it'll turn it to a higher energy yellow.
Yes. So this is the band gap, right? So let's say that this band gap gives you orange, because the drop from here to here corresponds to the energy of a photon that is orange. Well, if I cool the crystal, the band gap will increase. These two blocks will fit further away from each other.
Right.
And so now when an electron drops, it's going to be a bigger energy drop,
Right.
and it emits a larger energy photon. Okay. So that's the impractical way to tune an LED. The practical way is by changing the composition. Compared to gallium phosphide, the bonds in gallium nitride are what ionic? More or less? Gallium nitride is more ionic. Remember, ionic character is difference in electronegativity. So when you switch from phosphorus to nitrogen, nitrogen is more electronegative than phosphorus. Gallium is the same, right? So if you go from a slightly less to slightly more electronegative, you get a bigger difference in electronegativity between gallium and the nitrogen in this case. So it's more ionic. If the bonds in gallium nitride are shorter or longer? They're shorter. Nitrogen's smaller, so you're going to make shorter bonds. So if one of them is green, the other is blue, which is the blue LED? The gallium nitride. So shorter bonds or the more ionic character. Okay, both of them will help you gauge whether it's high energy or low energy. All right, so blue versus green. Blue is higher energy, higher band gap. Okay. So we've got this. I'm going to show you the graph in a second. So there's a graph at the below that shows you different compositions of gallium with phosphorus and arsenic, and their band gaps. And we'll just go through a couple of these and just try to calculate what we can calculate. So here they want us to look at A, B, C, and D. So here's a graph, and of course it's kind of off the screen. We have band gap here. We have the composition, the X in that formula here. So think about what this means. 0 for X. If I put a 0 here, that means there's no phosphorus. 1 minus 0 is 1. It's all arsenic, gallium and arsenide. So this is pure gallium arsenide. Over here, if X is 1, this is pure gallium phosphide. And then this is everything in between. So for instance, if I looked at A here, and I wanted to know what is the formula of the compound in A, so the formula is Ga phosphorus, so 0.2 is what X is. So phosphorus is going to be 0.2, and then the arsenic 1 minus 0.2, which is 0.8. That's the formula for this LED. The band gap is here. It's about 1.7 or so, 1.7 something. That's the band gap. And if I were to calculate what is the wavelength of the photon emitted from that band gap, well, this table kind of gives it away. It's 700 nanometers, which is squarely in the red. But you should be able to calculate it yourself. How do we do that? Let me remind you real quick. We have our band gap, or electron volt, to joules conversion. So 1.7 electron volts. I need to convert this to joules. 1 electron volt is 1.6 times 10 to the minus 19 joules. And let's see. So it's 2.72 times 10 to the minus 19 joules. And the reason we did this conversion is now we're going to use the equation for the energy of a photon. And the one that involves wavelength is energy of a photon is Planck's constant times the speed of light divided by the wavelength. And everything I plug into this equation, I have to have joules for the energy, and I need to use meters for wavelength. I'm going to rearrange this because I want to solve for wavelength. Alright, just move the E down, and if you want me to show you how I did the algebra, I can show you later. But Planck's constant, this is a constant you'll be given, 6.626 times 10 to the minus 34 joules seconds. That right there is why we have to have our energy in joules. Speed of light, 3.00 times 10 to the 8 meters per second. And then last is the energy that I just converted, 2.72 times 10 to the minus 19 joules. Let's see, 6.66 e to the minus 34 times 3 e to the 8 divided by that energy. I get 7.31 times 10 to the minus 7 meters. Notice you get meters in the end. And, you know, when we do wavelength of a photon, nanometers is a more useful unit, so let's convert it to nanometers. 1 nanometer is 10 to the minus 9 meters. You'll get, if I do sig figs, there's only 2 sig figs from the beginning. Right, so 2 here. So if I get 2 sig figs over here, it's 730 nanometers. And that's exactly what, oh, it's not exactly, they said 700. And I get 730, which is still red. Alright, red is 700, 800, something like that. So make sure you know how to do this calculation. But yeah, so we have our solid solution. You can see that for various amounts of the arsenic and the phosphorus, yeah, you get different band gaps. And it's not linear. I mean, it's on a weird curve here. That's not quite a curve, but yeah, you can get lots of different band gaps from that. Different color wavelength, different color LEDs, and so forth. All right. Engineering-wise, you know, you might get different results by how well your stuff is mixed together and how thin your layers are. And so, like, the construction of the LED has a lot to do with it as well. So it's not just a chemistry problem. There's a lot that goes into making LEDs. All right. How crystalline your material is when you deposit it on this. They make like thin layers of stuff, right? And they sandwich it with other materials. So that's more of an engineering problem at that point. All right. Any questions about this stuff so far? I think okay. So I want to switch to the next slide set, and we're still going to talk about current stuff, so don't worry. Nothing new. There it is. So just to remind you that the band gap in general, approximately 0 band gap gives you a conductor, a metal. Less than 3 electron volts is your semiconductor range, and an insulator is almost anything over 3 electron volts.
That's something we should memorize.
Yeah, 30 electron volts is probably your boundary, yes. Question, yeah.
Yeah, so does band gap give resistance in wire?
No. So this is another factor that we're kind of ignoring. But let me think if I can explain. So resistance is purely friction of electrons moving through the MOs. And it's beyond what I can really explain very well, because there is a temperature at which things become superconductive, and that is the temperature below which there is 0 resistance anymore. And so once you can get electrons starting to move, They will continue to move without any force applied to them.
Yeah.
But under normal circumstances, if you start making electrons move and then you stop the voltage, they'll stop. They will not keep going because of resistance. But yeah, the wire heats up because of friction. Like, yeah. So yeah, the resistance is kind of friction. I guess it's a little bit of. I shouldn't say that. I think it's probably a little bit of conductivity as well. So how small the band gap is, that probably applies as well. Yeah, I haven't thought about it too much. I can't tell you exactly. Sorry.
That's fair.
All right. So this is another slide that just reminds you that the picture here is pretty good. That the larger the overlap between orbitals. So here you got a small overlap because 10 atoms are gigantic, and so they have a long bond length. So the overlap's not as good. You get a small band gap as a result. It should be like nothing here. But if you compare that with carbon, which doesn't look like that much better, but there is more overlap, you get a stronger separation between the valence band and the conduction band. Remember, the valence band is all bonding MOs. The conduction band is all anti-bonding MOs. And so the better overlap, the bigger the gap between them. It's a big band gap. All right. Same thing. So I just kind of wanted to bring this up because this actually might be related to what you were talking about a little bit. How does conduction happen? Like, how do we think about conduction at the atomic level with electrons? So I already told you that. Let me skip ahead real quick. That when you have something with a small to no band gap or small band gap, most of the time the electrons are here. They're in the valence band, but if the material has any kind of energy, whether it's thermal energy just from being at room temperature, or if you apply extra energy, electrical energy, more heat, you can get some of those electrons to jump across this band, this gap, and be in the conduction band, and you'll have a conductive material, okay? So how many electrons do it? How do we think about that? So this is where I'm coming back to this diagram here, and we will see this again in detail later on. But this is called a Boltzmann distribution. Don't worry about the name yet. And let me kind of describe what you're seeing. So this axis on the x-axis tells you energy. This is labeled electron energy. You can think of it as atom energy too, kind of equivalent. And on the y-axis we have the fraction of electrons with that energy. So think of it as you can think of it as a probability almost, but just, how many out of the whole? Like you have a giant sample, how many out of that giant sample have that particular energy? And you can see that not very many have low energy. There's a whole bunch of them that have this mid-level energy. And as you get to super high energy, again, you get to small amounts of atoms that have that energy. Now, this is the most probable energy, the highest peak, but it's not the average. The average energy is here. You might be thinking, why is the average kind of not the highest peak? Well, that's because these distributions are not symmetrical. They're not parabolic. They don't make perfect U's. They start off here, then 0, they climb, they fall, but they don't fall to 0 quickly like that over there. They kind of taper off and just kind of get smaller and smaller and smaller out to infinity. And because they're not symmetrical, then the average is just to the right of the peak, basically. That's why the lines are there. So let's focus on the blue one quickly, real quick. The blue one is showing the distribution of energies for a material at 0 degrees C. And so, 0 degrees C is still warm. It's not absolute zero. So atoms have energy, but you've got all these different amounts. So some atoms have lots of energy, some atoms have a little bit of energy. It's not uniform. There's a distribution of energies. Most of them have this energy. Now, as we heat up our sample, if we heat it up to 100 degrees, notice what happens to the peak. The most likely energy shifts to the right, or the average, another way to look at it, shifts to the right. You get a higher average energy. But the curve kind of broadens out. It not only does it shift to the right, but it broadens out. So you get a bigger distribution of energies. And that's very typical. That's what we call, this is a Boltzmann distribution. That's what, you'll see that word again later on. So a physics person will vehemently disagree with what I'm going to say next. But the way we think of temperature, think of it as an average kinetic energy. That's what temperature is. It's not really, but that's the best way to think of it. An average kinetic energy. So the higher your temperature, the higher your average kinetic energy of your atoms are. Kinetic energy meaning energy of motion. So, why are we looking at this? Well, let's place the band gap energy for this material on this graph. And all it is a label. We're saying, okay, well, all these atoms, these electrons, have all these different energies. This is the minimum energy. That's the band gap energy. If the material has this energy, then the electron can jump up to the conduction band and conduct. So what fraction of your atoms or your electrons have this energy? Well, if you have the low temperature material, the area under the curve, this is getting to calculus a little bit, but the area under the curve over here is the number of atoms or number of electrons that do have the energy to bridge the gap. And if you compare this amount to the rest of it, it's a very small fraction. But as you heat up your material, this doesn't change. This is a band gap energy. That's not going to change. But as you heat up the material, the proportion of atoms or electrons that have the correct amount of energy to bridge the gap is now increased. So the area under the curve here is much bigger, and it's a much higher proportion of the whole material. So the idea is you take a silicon semiconductor. We had it at room temperature. We tested its conductivity. It was super weakly conductive, but it kind of was conductive. It beeped. I think I did it with you guys, right? Yeah. If I were to heat that thing up to 100 degrees, it would be a lot more conductive. And if I keep heating it up, it would be more and more and more conductive. Okay? So that's kind of how you should think about this kind of stuff. There you go. How would the conductivity of semiconductors change with increasing temperatures? I'm not going to turn it on. They will increase. Okay, we're going to. So if I compared a semiconductor to an insulator, and this might help to explain why an insulator, even though it has a band gap, it really isn't ever conductive. So here is an insulator. It'll have the same distribution of energy because it's at the same temperature as my silicon. But when I place where the band gap is, it's going to be way over here. It's not even on the screen because it's going to have a band gap that's like twice as large or something like that. And if you were to think, well, how many of those atoms have the right energy to bridge that gap? Practically none, right? Very, very, very few. And even if I increase the temperature, still not going to help. Yeah?
So just to be clear, conduction is when you've got excess of electrons on one at some point and a positive, a lack of electron at another point, and you send the electron through the material?
So conduction is when your electrons are mobile, are allowed to move around in the material. When they're in the, and I erased it, but when they're in the valence band only, so here's where I'm being very specific. In the group 4 material, the valence band is full, completely full of electrons. There are no empty MOs. And so if your electrons are just in that band, they cannot move to an empty MO in a neighbor because there's no empty MOs in a neighbor. So they're not mobile. They have to be in the conduction band so that they can travel to a neighbor's empty MO in the conduction band. All right, so that's the requirement for something to be conductive. You have to have mobile charges. So when you have ions dissolved in solution, the ions are what moves in solution. That's what makes conductivity through solution possible. But for a solid like a metal, the electrons have to be mobile. So metals are, the conduction band is like right on top of the valence band, so the electrons don't really have to go anywhere, they'll be conductive. For a semiconductor, the conductivity is proportional to how many electrons can get to the conduction band. So it'll be super weakly conductive when there's a small amount, but the more you get up there, the more conductive it can be. Does that kind of helps?
Yeah, it's more just about the electrons moving out of out of that one particular atom to a different one, rather than any
Oh,
particular
yeah, okay.
sort of thing.
Yeah, it's weird because the band diagram, it's all of the atoms together, and so the idea is, well, yeah, you're going from a delocalized model to suddenly localized, where you think, well, the electron has to move.
Yeah.
So that's where the disconnect is, I think. But
Yeah.
but it does have to be in the conduction band and have empty MOs to move to in order to be conductive. Okay. So again, the band gap for an insulator is way over here. If you tried to get to that energy, you would end up burning your insulator at some point before you'd even get it conductive. Yeah.
I was just curious, does this graph explain at all why electronics are heat sensitive? Or like,
Oh, well, so we'll cover that in the lab, but so for pure metals, they're already conductive. So adding more energy causes the atoms within to vibrate more, which will cause more friction with electrons. So adding energy, so making metals hot makes them less conductive.
oh, interesting, okay.
But for a semiconductor, making them hot makes them more conductive, more than the friction counters it. Yeah. You getting it? You kind of bridging the gap between maybe what you learned in physics? I don't know. There's a lot going on here. We don't have to learn all this for chemistry. I'm just kind of giving you the taste of what we could learn now. Like, we have the information, we have the tools to understand a lot more now. So we'll like I said, we'll cover those weird properties in the lab. That'll be like, hey, this is interesting. We'll go over, we'll look at photocells even. So that's like the opposite of an LED. An LED, we put electricity in, it spits out light. With a photocell, we absorb the light, and it absorbs light because of the band gap. Yeah. A specific light, I should say. Yeah. All right. So we're going to stop there. That's the max you'll have to ever know for the exam. Probably don't have any questions at the moment. If you do, please interrupt me. What I wanted to do next, because we have such a long time until the next actual new lecture, is just kind of introduce what we're going to do next. Just so you have something to look forward to, maybe. Maybe not. So we're going to talk about intermolecular forces. And we've already taken a peek at them because nonpolar solids, you know, like when you make dry ice, which is frozen CO2. Well, the molecule CO2 is held together by covalent bonds. But what holds together two CO2 bonds? Or two CO2 molecules? How do they stay together and make a solid? That's intermolecular forces. Graphite, it's actually one of the strongest materials if you consider the bond in the sheets. But between the sheets, it's like super slippery and there's hardly any bond. You can peel layers away. What holds the layers of graphite together? It's intermolecular forces. All right, so we're going to get into that. And it's not just in chemistry and bio, it's super important. On the left is a cartoon image of an enzyme. An enzyme is just a fancy protein that does chemical reactions inside. That's why it's called an enzyme. It catalyzes reactions. And the cartoon is, so if you don't know what an enzyme is, it's basically, if you've ever seen an amino acid, it's just a chain of carbon atoms that has a nitrogen on one side. Basically a small molecule. And a protein is just a super long chain of amino acids covalently bonded together. So if I took this and pulled it apart, it's just one long chain. Why does it look like that? It's folded on itself. it's because of intermolecular forces. There are some other forces besides just bonding forces that keep it in that shape. And those shapes, the way it's folded up together, is required for its function. If it wasn't folded that way, it wouldn't work. There's lots of genetic mutations that cause misfolding of proteins, and that results in like terrible life conditions for whoever has those mutations, you know? So the cartoon represents the way it's folded together, how the molecules are interacting with itself. DNA, all right, the backbone is phosphate and sugar, covalently bonded together. There are base pairs, these things stuck on the backbone, also covalently bonded. But DNA is two of these put together. Those two strips, those two strands are not covalently bonded together. They're held together purely with a really weak bond, which is not a bond, but it's called an intermolecular force. And if you've learned any biochem, any kind of bio, you might have learned Alice talked to grinning cat, adenine and thymine to go together, guanine and cytosine go together. Why? It's because they are perfectly matched to do intermolecular forces with each other. So this is like super, super important. It's like, even though it's one of the weakest forces in chemistry, it's one of the more important ones. I mean, they're all important, let's put it that way. So we're going to start off, and we're going to do it today, but we're going to start off by learning what organic chemistry, okay? So if you want to kind of go ahead and kind of learn about this stuff, we're going to talk about different kinds of functional groups, so kind of pieces of a molecule that make it behave a certain way. So what makes an alcohol an alcohol? What makes soap work the way it does? It's this thing down here. Well, that and a combination of that. And, you know, variety of things. So there's caffeine. We're going to look at functional groups. So there's these nitrogens, these amine things. What do they do? So that's what we're going to get to. We're going to start off with basic organic chemistry, and then we'll get to the intermolecular forces. So we'll talk about liquids and eventually gases. So it'll all kind of lead to all the different phases of matter that are interesting. Well, that are easy enough to be studied. Like plasmas are interesting too, but they're hard. Anyway, that's all I want to go over today. Do you want to start the practice exam for the next 10 minutes, or just going to just stop? Okay, no, if you want to stay, you can do it. It's 10 minutes, so at least you can get a sampling. Yeah, we'll use straight to the word problems. Let's do that. Oh, where is it?
So how would you design a battery, by the way? I was watching something on the internet about batteries.
Battery.
Yeah. Like lithium-ion batteries, what's the next step?
So this is a very 223 question, because we need to understand equilibrium to really talk about it very well. But liquid batteries are difficult because of the liquid and because of concentration. As the concentration of compounds changes, your voltage will drop.
Right.
So solid state batteries are more reliable. But then when you do solid state, you have it's hard to do reactions in solid state because crystal sizes can change and cause things to expand and contract, and they don't mix as well. So you need to design it like you make thin layers, and so batteries, if you open up a battery, it's a layer that's kind of rolled up, like a flat layer that's rolled up into a silicon cone.
Right,
or
got a
silicon.
few layers of paper around it.
Yeah, there's a lot going there. But, and then you have to look at the voltage potential between it's about electron transfer. So you're transferring electrons. That's what causes the battery to work the way it does. And the two components that one thing transfers electrons to the other, you have to get the right ones that give you the right voltage you want. And then, is the reaction reversible? If it is, then you can recharge it.
Right.
If it's not, you can't recharge it.
Yeah.
So there's a lot that goes into it. It's a very much an engineering problem. Okay, sorry.
Did you say LEDs aren't gonna be illuminated? Or
They are.
They are.
They are.
So like problems where you're given the band gap energy and then you find a wavelength?
Yeah, just that stuff. I mean, and then like, what would the color of the LED be
Yeah.
if I replaced this, if I replaced gallium with aluminum?
Okay.
Things like that, you know? You can figure it out. Alright, so, here's some short answer. Identify the bonding within this compound by locating each of the bond type triangle on the next page. Use the letters to describe as ionic, covalent, metallic, semi-metallic. Oh my god, okay. This is the worst one to do on the board. So, CO. Here, I'll just write them down real quick.
Oh, what was ammonium carbonate, by the way? What's the
We're done with the test. Okay.
-2,
Ammonium carbonate is NH4.
plus, and then CO3, -2.
That's
Yeah.
carbonate. So crisscross. That's it.
Close.
It looks so weird.
It's all or nothing on those, right?
Yeah, it's extra credit. ALAS, CUZN, and then carbon. Okay. Oh, and I don't have a table of electronegativity, Sandy. All right, let's skip this one. You guys can do it at home. This one's not that hard.
Will we be given it?
Yes, yeah. I believe it's like in the front. And if not, I will give it to you. Maybe this doesn't have it. But basically, yeah, you look up electronegativities, you do the difference, then you do the average. If it's one single atom by itself, then just compare it to itself. So the difference in electronegativity is going to be 0. The average is going to be whatever it is. And then you kind of plot out the bond type triangle. And you kind of figure out what the bonding is based on where it ends up. Alright, I think that one's not too bad though. So 39. These are ionic. Let's order them from lowest melting point to highest. So I focus on the charges first. Always look at the charges first, because the charges have the biggest effect on the melting point. And when we say melting point, we mean the strength of the ionic bond. The higher the melting point, the stronger the ionic bond is going to be. So Mg is a +2 ion, O is a 2- ion, Li is a +1, F is a -1. Here we've got a +1 and a -2, so kind of halfway. And RBI, it's not Runs-Meted, it's +1 and -1. So that's the strongest. That has the highest melting point. This would be next because it's got a +1 charge with a -2 charge. And then it's a tie between these two, sort of. So if the charges are the same, then we look at size. So rubidium is big, iodide is big. Big atoms make long bonds, and we know that long bonds are weaker. So this would have the lowest melting point, the weakest bond. This is higher. So it goes RBI, then LIF, then K2O, then MgO. I explained in the key that this one is not exactly on the exam, because I give you this molar volume instead of something you guys are used to. But you could calculate density from this too. I'm going to leave you to do that on the key. But here, let's look at this one. I've got this weird. These are a little hard. I'll say that. Okay, they're not the kind that you might see in the exam. But here's a chalcopyrite structure. This is another material used for LEDs, so not just the diamond stuff that we've been looking at. What is the formula? Oh, lovely. So you need to know. I mean, your lab stuff is going to help, right? So we count, and you can look at this if you want. I like to look at the layer diagram. So Z0, this is the bottom and the top layer. These are definitely corners. And they count twice because we're going to do the top layer as well. So there's 8 corners, and they count as 1/8. I should say the white atoms, okay? And so there's 1 total atom from the corners. There is also a face. And it's white. So there are 2 faces, right? So the bottom layer and the top layer. So there's 2 of these, and each counts as a half. So we've got 2 white atoms so far. Now let's go to the next level. This is inside. This is like right here. These are both inside. And let's just do them all together. So these are all inside. So 1, 2, 3, 4 black atoms inside. 1, 2, 3, 4. Let's call it gray. 4 inside grays. And then 4 inside. I can't spell today. All right, and then let's go to the rest of the white atoms here. So this is where it gets a little tricky. That looks like a face, and it is a face. That's these. So 1, 2, 3, 4, 5, 6, 7, 8. That's the top layer here, the 8 faces. 8 face times a half is 4. That's the white ones again. And then the ones I didn't do is this one. That is not a corner. That is an edge. Okay, so an edge, 1, 2, 3, 4 edges. And each one of the edges is a quarter. And then there's the one inside. This is a really weird way of doing this. I probably could have organized things better. All right, so if I count everything for the white atoms, there's 1, 2, 3, 4, 5, 6, 7, 8 white atoms. And what were the white atoms? They're the seleniums. There were 4 of the black atoms and 4 of the gray atoms. So 4 coppers and 4 indiums. So those are the total number of atoms inside the unit cell. Let's reduce this to a more simplified formula. 1 copper, 1 indium, 2 seleniums. That is the formula of the compound. How is this structure related to zinc blende? It's actually 2 zinc blends kind of stacked on each other. Notice that these are in tetrahedral holes. These are in half the tetrahedral holes as well. We just have, they're just opposite orientation. So instead of like this is in the front right, here this is in the back left now. So just kind of mirrored images almost. Anyway, it looks like 2 zinc blends stacked on each other, basically. All right, we've run out of time.
Wait, so generally, would you accept if we just looked at one and said it's a face-centered cubic, so there's four white atoms, and then the other 4 are inside, so there's 2 black and 2 gray, and then it just repeats itself because it's a unit cell? Or is that
Sort of, but it's not a unit. So this is by itself is not a unit cell.
Yeah.
Because this does not repeat here. But
Oh,
yeah, you could infer it that the way you said it works. It's just
But if you said to show your work, then you told it.
yeah, you have to do the whole. I mean, some better, maybe less messy than I did it. But yeah.
So,
Looks like
so
how I was done.
is that considered a solid compound or a solid mixture? I think you called it.
No, this is crystalline. I mean, it's not a solid solution. It's I mean, in a solid solution, you're not going to have. It's going to be crystalline, but it won't be exactly the same atoms in the repeating unit cells across your crystal.
Yeah, true, like that maybe. I mean, it's not.
Well,
repeating.
this is if it's pure this is pure crystal. This will be the same unit cell throughout.
Oh, true. just
The
like that.
solid solution would be you're looking at the crystal, and occasionally, instead of a selenium, you'll have a sulfur somewhere, for instance. But it makes the same structure. Just occasionally a selenium is replaced with a sulfur. That's what a solid solution would be.
Oh, interesting. Okay, so for this, you would be 100% sure that it would always repeat like this.
Always be like that. That would be the pure crystal version, yeah.
And so how do you express the unit cell for a cell solution? Or I guess there would be no unit cell.
Well, yeah, it's not a pure crystal in a solid solution. So I guess you would just say that the unit cell has this form, and like you could replace this part with this throughout. You know, I don't know. There's probably a better way to do it. We're not going to cover that.
Is the workbook stuff from this week going to be due on Thursday? Then?
Oh yeah, since we're only going to be here Thursday, yes.
Okay.
Yeah, don't bother coming in.
Turn it in.
Knocking your door on Tuesday.
Not in the mail today.
Sorry, okay. Do my homework.
Sure, we should get extra credit for you that.
It's not a day off for me. I have to go to stupid online meetings and stuff. So.
Yeah, that's not bad. Well, enjoy your meetings on Tuesday.
Yeah.
Well, you have a question.
Yeah.
Just when you're talking about activity and stuff,
Mhm.
I was just kind of curious, like, what is kind of the models we use for describing that?
Describing it?
Right.
I don't know. All I know is there is a temperature called the Curie temperature. That's what it's called. Below which a material that wasn't superconducting suddenly becomes superconducting. And you know, when we say, oh, buy this superconductor, when there are no room temperature superconductors, they don't exist. So all superconductors, you still have to cool them down. It's just some of them are manageable. You can cool them down, you know, with liquid nitrogen. Some materials, to make them superconducting, you have to cool them down to near absolute zero. So that's not practical. But yeah, there is a temperature within these materials below which suddenly the resistance is zero for electrons to move. And because of that, you get all these weird effects where you get these currents that just, if you can generate the currents of electrons, they stay going. They don't stop. One function of superconductors, besides the magnetic field, is storing energy. You can cause the electrons to start moving and fast. You know, you can store energy like that. It's not practical, but I know that they do that for things like NMRs, nuclear magnetic resonance MRIs, same thing. So they use the magnetic field too, but they also generate pulses of, I don't know how they do it, but these radio frequency pulses that cause your electrons and whatever you're scanning to just bend over temporarily. Yeah, we use superconductors in a lot of things. You have to have everything stored at low temperatures before it can happen.
Put in more energy than you save.
Oh, it's big waves, yeah. But so you need a reason to use superconductors, but they're a lot of fun. And there's plenty of research going on to try to find room temperature superconductors. So if we can do that, oh, it'll be so nice, you know. We can make maglev rails that don't require a lot of work to keep working, you know. Yeah. Anyway, do you have a question?
I do. And
Yeah. Okay, we can move over.
Yeah, for you're playing on the
$10 on Tuesday?
yeah, that's like very
I will try to do that. I have an appointment
I don't know when that's going to go in favor. Nobody says Indigo.
Okay, well, yeah. No worries, you can't make it.
How long are you going to do it?
I'll probably be there until 3 or something. So.
Okay, I'll try to slip in then. Thanks.
Whew.